Okay, in this problem, we need to consider whether or not the system is going to move. We know it wants to move this way because this gravity force is more than this component of gravity, but is this gravity force enough to overcome the static friction force in the problem? Let's first figure out that. So maybe we'll think about the system as being this flattened out system. Here's my kind of system. I'm going to flatten it out to this kind of system here, where I have the 10 kilogram mass here and the 10 kilogram mass here. The force kind of pulling the system in this direction is this Fg, and the force pulling the other way is Fg parallel, I'll call it G parallel, and that's going to be Fg, that's this component here, Fg parallel. And there's also a friction force opposing this. So the static friction force is a friction force that's static. Let's just see the net force with those three forces involved. So we'll say net force equals, I'm going to make this way positive, this way positive, is Fg, the 10 kilogram one, is Fg here, minus the Fg parallel, minus friction force. Okay, what are those forces? Well, there's mg of the 10, so 10 times 10. There's the gravitational parallel component. All right, well, that's going to be mu, because it's static, 0.3 times Fn, which Fn requires a little bit of drawing of triangles. So there's this component here of gravity. That component is being balanced by the normal force right here. And so then if I put my theta 16 here, this dotted line is the cos, is the adjacent to this side. So that component there is going to be mg, put mg for now, mg cos 60. That's the friction force, and I got to minus the parallel force. I've rearranged these terms, unfortunately, minus the component of gravity mg sine 60. Okay, and when you do the numbers, it does look like this net force value is going to be negative. That means the net force is kind of to the left. Now, friction actually won't pull it left, but it means net force is actually 0. Now I could have read the problem. It does say the box remains at rest, but yes, the calculations do support the fact. Let me just go over that one more time. Because net force is negative, it means net force is this way. If net force is negative, that means therefore there's no acceleration. No acceleration. And that is what the problem predicts. How about the friction force? Well, the friction force then won't be this big, will it? The friction force is going to be just enough to balance everything else out. When the net force is 0, so we'll do a little bit of rearranging here. Net force is now 0. The forces are still going to be the gravity force minus the Fg parallel minus the friction force. So the forces on my system, gravity this way, close gravity, gravity 1 maybe, gravity 1, gravity parallel, 2, friction. So I can now plug in my numbers, same as before actually. So it'll be 0 equals m is 100, sorry, m is 10, g is 10, this is 100, minus the parallel force is 100 times sine 60, and this guy's my friction force, that's my goal. This is 0 equals 100 minus 71.6 minus friction. So I move this around, I get then that friction equals this difference, which is about 18. Okay, what made a math mistake there? 100 sine 60 is actually 82.6. Then when we do the minusing here, the friction force will be 86.6, sorry. More mistakes. The friction force will be 13.4 newtons. And that rounds to the answer, just in the 13 newtons. It's about equal to 13. Oops, that's part B. Part A, the tension of the string. Well, once I figured out the acceleration is 0, A initial is 0. Then the tension is being balanced by the gravity force. So if you think about the force diagram of just this box here, that guy's force diagram is tension minus gravity, or gravity, no acceleration, so they're equal to Fg. And gravity is G is 10, mass is 10, so it's 100. Okay, the string is cut. So now we have a new system where this is of a mass falling along a ramp, and determine the kinetic energy of the left-hand box when it reaches the bottom of the plane. So we can let's use energy conservation to solve this question, just because we can. So there's no longer any string. This is cut. It's here. And we could just do it a couple ways. We can say, hey, I'm going to figure out the acceleration of the box. I'm going to find Bf using this equation here. Once I have Vf, I can convert that to kinetic energy using half mv squared. That's perfect. That'll work just great. For that one, we need to figure out the gravity here, this component, and there's going to be friction as well. But instead, let's try using an energy conservation argument instead, just to keep our energy solving problems fresh in our mind. So the energy is conserved. So energy at the top, the energy T top equals energy total at the bottom. And what kind of energy do we have here? At the top we have just potential energy. Bottom we have kinetic energy. But some of the potential energy also became heat. And the heat is the work done by friction. Okay, so the total top energy is mgh. mgh. That's going to be, h here is going to be the height. That's going to be the h. Heat here. And what does it become? It becomes kinetic energy. But it's also, as it falls, it creates heat. So some of this energy at the beginning becomes that, and it becomes heat. I mean, think about heat as being the work done by friction. This is the work by friction. That's going to be the friction force times the distance. And that d, that distance there, will actually be this distance, this gap here. That'll be the 2. Here are our numbers here. So the friction acts over this whole length. That's number here. The height is just this gap here. It's this gap there. Okay, so now we're ready to start plugging in some numbers here. 10 times 10 times h, we'll get h in a moment, equals half 10. Oh, actually our goal is kinetic energy, so we have to leave this as Ke. This is my goal actually. My goal is the kinetic energy at the bottom of the ramp. Plus heat, work done by friction. It's the force of friction, which is mu Fn times 2. Okay, let's figure out these two unknown pieces. So first let's figure out the h. Let's draw this triangle down here. So we have the 2 meter piece. This is 60. We want to find the height. Well, sine 60 equals opposite over hypotenuse. So h equals 1.732. So I can put that in here. 1.732, my h term. How about the friction? We need a force diagram for this guy. So we have our ramp, nice big force diagram. We have our box, we have our gravity, we have our normal force, we have our friction. We need the normal force. So we're going to look at this problem. We're going to look at this problem in kind of this dimension here. We're going to say, hey, this component of gravity, this guy right here, that component of gravity, we call it FB perpendicular, equals a normal force. So if you can find that guy, we're set. And this is the 60 up here. So in this triangle, we have the gravity, we have the component of gravity this way, and the component of gravity this way. This is the 60. That guy is Fg times cosine 60. It's the adjacent side. So then our Fn is Fg cos 60. And cosine of 60, we write triangle 1, root 3, 2, 60 goes here. Cos 60 is half. Then Fn is just 50. Fg is m times g, 10 times 10 times half is 50. Okay, good. So then Fn is 50. So I can replace this guy here with mu, which is the 0.15 times the 50. 2 doing there. Oh, times g. That's friction times this here is friction. So if we do the math here, we eventually end up with kinetic energy being equal to 158 newtons. Then this is the, I guess, 2 sig figs probably. So actually, officially, it should be 160 newtons to 2 sig figs. Okay, that's it.